Now, our next speaker is Professor Kabir Ramola from TIFR Hyderabad, and he will be talking about bunchwise balance and irreducible sequences in the light-heavy model. Professor Ramola, over to you.
Yeah, I am, as a graduate student, I was with Deepak, and many times I think between all of us students, we keep asking the question, but would Deepak think this is trivial? And so that has sort of made us look for more non-trivial models. And so thank you, Deepak, very much. And Mustansir as well. So today's work I'm going to be describing is a collaboration with Mustansir, and he's worked extensively in this particular model. And so we found some new results in this particular model, which I'm going to describe. So the title of my talk today is Bunchwise Balance and Irreducible Sequences in the Light-Heavy Model. Just a second, yeah. So the models that I'm describing today, or this particular model, is one in a class of models which describes fluctuating local drives. And these are models that describe systems that break detail balance at the microscopic level. And even though many of such simple models are built with very simple local rules, exact determination of their non-equilibrium steady states has been hard. And these kind of models, which have fluctuating local drives, have of course grown in prominence over the last few years because of their connection to active particle systems that indeed break detail balance at the local level. And having an emerging understanding of what kind of non-equilibrium phases and steady states can emerge in these systems is therefore important to sort of classify non-equilibrium physical systems in general. So several key questions about the dynamics of such systems remain open. And of course, many models can be described in 2 and 3 dimensions, but in order to get exact results and find some exactly soluble models or exactly determinable non-equilibrium steady states, it helps to look at one-dimensional models. And in this class, particles that are coupled to a fluctuating surface have proved as very useful tools to characterize such behavior. And this is a field that Mustansir has worked extensively in. And so this is one of those classes of systems that I'm going to describe. So just as a outlook, this is the well-known master equation, which describes the evolution of probability distributions in time in configuration space. So probability P C of t, which is the probability that a given configuration is occupied with a given probability at time t, evolves because there are transitions between configurations that are described by this master equation. So the master equation basically describes the rates of transitions from a configuration C to C prime. And for configurations C not equal to C prime, you have some given rates. And of course, the diagonal terms have to cancel. So the diagonal terms have a summation over the rest of the configuration. So this is a very simple known equation that governs the probability distributions in configuration space. And you can then describe configuration currents, which are basically the rates of outgoing transitions multiplied by the probability of occupation of a given configuration. So here I'm describing JC to C prime, which is just the probability of occupation of a given configuration and the rate of transition from that configuration C to C prime. And similarly, the incoming transition from a configuration C double prime is given by this formula. Yeah. So in this talk, I will be focusing specifically on particular balance conditions which are obtained in the non-equilibrium steady state. Why would we want that? Because in the non-equilibrium steady state, the probability distribution doesn't evolve in time. And so if such a condition is valid, then the currents outgoing from a configuration and the currents incoming to the configuration must balance out. So that is expressible in terms of the rates of the configuration currents being balanced, incoming and outgoing configuration currents. And so this is the main focus of my talk today. How and when can you create such steady state balance conditions? Are there some specific and special conditions that can lead to steady state balance? And can we come up with interesting models where such balance conditions can be exactly determined? So in general, this is a very hard problem because the configuration space is exponentially large. So finding steady state balance conditions where you can prove exact results is of interest. So steady state balance can occur in many forms. I'm going to just describe a few. One of them is the well-known detail balance, which is from one configuration C to C prime, the current outgoing and the current incoming are balanced. So this is very well known in equilibrium statistical mechanics as well. A less well-known condition is pairwise balance. That is, you take a configuration C that you are at, and the probability current outgoing from C to C prime is exactly balanced by a uniquely determinable configuration C double prime, which has the exact same incoming probability current. When such a condition can be satisfied, then you still have microscopic steady state balance and leading to a non-equilibrium steady state. In this talk, I am going to introduce to you a new kind of condition called bunchwise balance, where you don't just have a uniquely determined configuration for every outgoing transition, but you can have a bunch of configurations that have an outgoing probability condition that are balanced by another bunch of configurations which have an incoming probability current, and each of them are uniquely specified, and they provide a unique cover of the configuration space, and because of that, the steady state microscopic rate current balance is satisfied. In addition to having probability current balance, you can also have some special conditions called microscopic rate balance. For example, if the rates in the master equations balance themselves, then trivially you can show that you will have an equiprobable steady state, because in the non-equilibrium steady state, if every configuration is equally probable, then the configuration, the probability current is trivially balanced. So this is a special condition not included in the probability current balance, but we are focusing specifically on these rate balance conditions, and I will introduce to you models in which you can do that. One of those models is a very well-known model which is discussed many times in this conference, which is the asymmetric simple exclusion model. So in this model, you have a single species of particles with biased motion and hard core exclusion, and biased motion to the right is different from the motion to the left. So the probability of hopping to the right is, let's say, half plus A, and probability of hopping to the left is half minus A. This has hard core exclusion, so particles cannot hop to a site which has another particle. So physically, this exclusion constraint mimics short-range interactions amongst particles, and the asymmetric exclusion process has been used to model all kinds of systems, including transport and low-dimensional systems. And I would be remiss if I don't mention Deepak's seminal contribution to this particular field, where he was able to show that the Bethe-Ansatz can work in this situation. And so the asymmetric exclusion model actually has a very nice balance condition, which is pairwise balance, which was introduced by Professor Barma as well. And in this case, for every configuration in the ASEP, the outgoing probability current to a configuration C prime is balanced by an incoming current from another configuration C double prime. How does that work? So let me illustrate that. Let's take a configuration of the ASEP. Suppose you are going to update this configuration. The particle at the rightmost edge of this cluster will hop to the right with probability half plus A. Now, if you were to reverse this transition, that would happen with rate half minus A. So clearly, detailed balance is not satisfied. But it's trivial to, so it's easy to show that you can just go to the left edge of this interface, of this cluster, and find a hop to the left, which is happening with probability half minus A. And that will then have a hop to the right with a probability half plus A. So this incoming transition to configuration C will be balanced by this outgoing transition to configuration C, from configuration C. So you can identify this C prime to C double prime, which balances exactly the rates. And so in this case, the rates are balanced exactly. And so you can show that you have equiprobable steady state. And this, just so that it's easy for me to introduce the next step of what I'm going to show, it makes it convenient to try to represent these configurations in terms of these brackets that I'm showing. So the interface is given by this left bracket and the right bracket. And so every time you have a left bracket and the right bracket, you can say that these two are pairwise balanced. And so I'll just call these kind of brackets interfaces in order to introduce the next model, which is light heavy model, which has been studied in detail by Mustansir. So in this, it's a generalization of the ASEP where you have two species of particles, light and heavy, interacting through a fluctuating membrane. It also models sedimenting particles in a viscous liquid. So in addition to having particles and empty sites, you now introduce particles which are represented by these black sites and holes, or bubbles, which are represented by these white sites, and you have interfaces, which are basically represented by tilt fields that I've shown here. And an equivalent representation of this model is basically hills and valleys and particles sitting on hills and valleys. And the microscopic evolution rules are very natural. You have, if there's a particle which is represented by this black side, and you have a left tilt or a right tilt, the particle will roll downhill, biased with a rate half plus a, and it will roll uphill with the rate half minus a. But in addition to that, the particle can also cause the surface to bend, and so a particle will create a downward bend with a rate half plus b, and the opposite rate will happen with half minus b. But in addition to that rule, you can also have bubbles which will now try to push the interface up or the surface up, and that is biased with the rate b prime. So this
Professor, you have 1 more minute.
Okay, sorry. So this model has many non-equilibrium phases, which I won't go into, which Mustansir has worked in detail on. And in this case, we can, so I'll just generalize, give me 1 more minute. I'll just generalize the pairwise balance mechanism in this case, where you have, in addition to having interfaces, which were represented by these brackets, you can also have bends, which are up tilts and down tilts, which I'm representing by these triangular brackets. So in this case, when I had a pairwise balance condition, 2 brackets were able to reduce to give you pairwise balance. But in general, if you have 2 kinds of brackets, which are interfaces and bends, then it's not always the case that you can you can reduce them into pairwise balance conditions. And in this case of the LH model, you can show that if you use these rules of pairwise balance, you will end up with irreducible sequences of interfaces and bends separated by long sequences of clusters. And in the generalization of this pairwise balance mechanism, you can show that the net probability of an incoming and an outgoing transition depends on just the irreducible sequence. And we basically showed in this model that the rates of the incoming and the outgoing transitions can be shown to be only dependent on the irreducible sequence. And when this condition is satisfied, that the bias rates that are introduced in the LH model, 2a plus b prime is equal to 0, then the rates balance, but in a very, very special way, where two outgoing transitions from a given configuration are balanced by 2 incoming rates from another configuration, another set of configurations, but those are not the same. And here is a summary of what happens. So in the simple exclusion process, you have detailed balance. In the ASEP, you have rates incoming and outgoing balanced from C to C prime. Whereas in this LH model, using these irreducible sequences, you can show that you have a bunch of incoming and a bunch of outgoing transitions that are all balanced amongst each other, leading to another non-equilibrium steady state. And in the LH model, you have a bunch of 2 coming in and 2 going out. But in general, you could have a bunch of larger sets of transitions. And finally, these irreducible sequences that we defined also lead to a coarsening length scale, which is quite a remarkable sort of observation, which we are looking more into. And in summary, we were able to show an equiprobable measure on the configuration space of this new LH model, which provides a product measure steady state. And this bunchwise balance mechanism, although we found in the LH model that it has 2 incoming and 2 outgoing transitions, it would be interesting to find larger bunches. And recently there has been some work on this kind of balance mechanism as well. And in summary, thanks and congratulations to Deepak and Mustansir. It's been a pleasure working with them. And yeah, take questions.
Thank you, Professor. Questions?
Yeah, may I ask?
Yes, please.
Yes.
2 questions. One, in the light heavy model, you have two parameters, B and B prime, B being how a heavy particle makes a hill into a valley, and B prime, how a light particle makes valley into a hill. Do you get any simplification in your result if B is equal to B prime? It didn't look like it, but...
Not in the particular result that we are looking at, but when B is equal to B prime in the phase diagram, you do have exactly determined in steady state, but not in the bunchwise balance mechanism. So the bunchwise balance when you have here is B equal to B prime, sorry, 2A plus B prime is equal to 0.
That's all.
So the bunchwise balance is not simplified, but you can have other simplifications not from the bunchwise balance mechanism.
I see.
You're right, yeah.
I forgot my other question. I'll let other people ask.
There is one question in the chat from a way to know a priori how big a bunch do I have to look for simply from the dynamics?
No, that's not clear from the dynamics. In fact, you have to find it based on the microscopic rates, and it's not clear that you will always have a bunchwise balance scenario. In fact, in this LH model, we were only able to show a specific plane in which the bunchwise balance mechanism holds, as you can see here. So this red plane that I'm showing in this generalized three-dimensional phase diagram has a bunchwise balance mechanism, but nowhere else does it hold. So it's not a priori clear. Yeah. So yeah.
So it would just a comment.
Yeah, sure.
It would look like if you want to make the rates add up to some other set of rates, then the condition that A plus A prime should be equal to B plus B prime places a lot of constraints on the number and the possibilities.
Yes.
That's all.
Okay. Yeah. So absolutely. In fact, so as I was showing here, and I had to skip it a little quickly, is that the incoming and outgoing rates from these identified configurations, C1, C2, and C1 prime and C2 prime, actually equals this 2A plus B prime. So only when this condition is satisfied do the incoming and outgoing rates cancel out. And so yes, it definitely places a very large constraint on the parameter space. And as Deepak is pointing out, it only occurs in this special special plane in the parameter space. Yeah.
Okay, thank you.
Sriram Ramaswamy has a question.
Yeah, you very quickly showed some coarsening laws. The original model we wrote down had a log T, and you're showing various other coarsenings here.
Yes.
So do you actually smoothly go from one of these to the other as it changes?
Yes. So this is sort of recent work by Mustansir on the several different phases that occur in this model. And you can tune, for example, you can go from any of these states. So this is strong phase separation is what
as the log,
but you can go to any of these phases, infinitesimal current, finite currents. And in fact, you have this very interesting fluctuation dominated phase ordering that Satya and Mustansir and people have been looking at recently, which occurs in this model. And in FDPO, if I go here, you actually see very interesting exponent of 0.11, which also shows up in this coarsening length scale of the irreducible sequences. So there seems to be some connection, which remains to be explored.
Okay, thanks.
There is another question from DDA's office.
Yeah. So I had a question about Kolmogorov criterion. So, when you have systems where you don't know the probability distribution in steady state, but still, you can use this criterion that you think of rings of configurations in which forward rates multiplied and the backward rates multiplied equate. And then you can sort of say that the, detail balance holds, that's a checking condition. So I was just wondering, now that you were talking of these bunchwise balances, so what happens to Kolmogorov criterion, and are there equivalents of those sort?
Yeah, absolutely. That's a very interesting question. But in this case, I don't know what the generalization of that would be. But here, you actually don't have forward and backward rates from the same configurations. You have forward rates from one set of configurations. Sorry.
Yeah, I know. Even for pairwise balance, that would be the case.
That even in pairwise balance.
Yeah. So, but then, I have always wondered that, in such situations, for example, for pairwise balance, if you have specific rings, then you can, of course, talk of similar criterion.
Yes.
But it would be nice if for this kind of balances, if one can come up with conditions with simply rates, because then we don't have to worry about probability. That's the point I was.
Precisely the point. And
I have been,
Just to clarify, does this mean that the original Kolmogorov criterion of a triangle does not get satisfied for bunchwise balance and
or pairwise balance? Yeah.
Or pairwise balance, right?
Yeah.
But Dipendu is asking, is there some other variant of the criteria?
Yes. That is what I was, means it should be generalized to some other, it could be. I mean, I don't know. And if it is done, it will be very useful, because I find this Kolmogorov criterion very practical use for many problems where you cannot solve the probability distribution, basically.
Exactly.
Yeah, thanks.
Yeah, so it would be very interesting to sort of look at this, the generalizations of that. Yes. Hi, Mustansir.
Mustansir Verma?
No, I just wanted to say Kolmogorov is very useful, but then you have to look at every loop possible. And it's useful to show that things are not in detailed balance, but it's not so useful.
Right.
Otherwise.
Yeah. But even the reverse is often very useful, right? I mean, that you can show that there is one violation, then you can show that it is not.
No, absolutely.
You know, so that is what I'm. So similar such criterion would be nice to evolve. I mean, I don't know. Yeah.
Right.
Okay, thanks.
Okay, if there are no more questions, let us thank the speaker again.